Well, good morning, everyone, and welcome to this session of Shape Your Future, Careers in STEM. My name is Camille Thompson. I run the STELR program here at the Academy of Technology and Engineering. And as we gather for this meeting from different places around Australia, I'd like to acknowledge the traditional owners on the lands on which we meet. I'm joining you from Ngunnawal and Ngambri land here in Canberra, and I pay respects to elders past and present and to any Aboriginal and Torres Strait Islander people who are joining us online today. And we acknowledge forever the knowledge embedded in country as we are talking about our knowledge that we have learnt through our Western systems. And today we have Dr. Ben Sparks, who is going to talk to us about his work in quantum and about fantastic stuff he's doing, and also his career journey with us today. Remember, you can ask questions at any time through the Q&A function, which is at the bottom of your screen. We'd prefer you use that rather than the chat. It's a little bit easier for us to see it, and we will answer it either as we go along, or we will have a Q&A section at the end of the talk. So any questions that you want to put in, all questions are good questions, and we'll endeavour to get through them all at the end of the chat. And as well, you'll be sent a feedback survey link at the end of this, where you can give us some feedback on what's worked and what you'd like to see in future sessions. And you also should have received an extension worksheet as well. So if you haven't, please contact STELR admin for that. But without anything further, I will pass you across to Ben. Good morning. Good afternoon, Ben.
Yes, good afternoon. Hopefully you can hear me fine. Yes. Yep. Excellent. Cool. And hopefully you can see my slides.
We've got the presenter view on it, so you might be.
Oh, sorry, I could get the other one. Yeah. This is, oh, that's always how it goes, right? You get super organized. Oops. Sorry. I'll just try this again. I've lost my Zoom window. Sorry, everyone. This is science in action. Where is Zoom gone?
It does trick you like that.
Here we go. Okay, let's stop sharing this one, and I'll start. Let me put the PowerPoint up again, and I'll share a thing. And then I promise we actually get started and hopefully talk about some science. Okay, share screen, share that screen. Okay, hopefully now seeing the actual slides. Yep.
Yes.
Yes, brilliant.
Definitely
okay.
Seeing that.
Fantastic. Sorry everyone about that. I'll start by thanking you all so much for being here. I'm really excited to be here presenting to you today. My name is Ben Sparks. I'm a quantum technology researcher with the Defence Science Technology Group, DSTG, and I want to start by saying that I love my job. What I want to today is give you, firstly, a bit of introduction to the organisation I work for talking about the work that I'm currently doing, then the career path that I took to get here. So I think the first thing I want to say about working for the Defence Science Technology Group is that there's a common misconception that we are part of the military because we're part of the Department of Defence. And the short answer is we're not. So there are two parts to the Department of Defence. There is the Australian Defence Force, which is the Navy, the Army and the Air Force. And these are people in uniform, people you would have seen recently helping out with the floods in northern New South Wales and Queensland. Then on the other side of this graph, there is the Australian Public Service. And there are actually 9 different groups within that, within the Department of Defence. And just one of those is the Defence Science Technology Group. So we're civilians like anyone else. We can quit our jobs anytime that we want. Though as you'll hear today, that's something I'm definitely not going to be doing anytime soon. Now, this is a slightly old slide, but there are about 2,800 people working for DST at the moment. And especially for our Victorian listeners, the 2 main sites for DST are here in Adelaide, where I am, at Edinburgh, but also at Fisherman's Bend in Melbourne. And I definitely recommend if any of you get a chance to go down and visit them, they do some pretty cool stuff. So if you can get on site, definitely worthwhile doing. Now, DST have, I guess, 7 different what they call divisions, working on a number of different cool technologies. So we have 1 division each for the different services, so maritime, land and aerospace, and then 4 different divisions that sort of go across everything. And my work here is based in the cyber and electronic warfare division. Now, while I'm a physicist, a quantum physicist, there are many different types of research being done at DST, and not all the research that we do is just for the Australian Defence Force. A lot of what we do benefits Australia as well. So maybe the most well-known example of, I guess, work by DST that's helped people outside the Defence Force is the black box flight recorder. And that was actually built by Dr. David Warren in the precursor to what is now DST back in 1953, so a while ago now. In a more recent example, what DST has done to help the Australian public is our work during the COVID-19 epidemic. At the very start, 2 years ago, which seems like forever ago, when this first hit, we were lacking a lot of personal protective equipment, or PPE. And as part of the sort of whole of government response to COVID-19, a lot of DST personnel were critical in, I guess, rapidly prototyping and then manufacturing PPE for our frontline health workers. And the turnaround here was only in about 3 weeks, which for science is pretty impressive. And this also means that to do these things and achieve the impact that we do, we have scientists from all across the spectrum. So we have people who are chemists building new sorts of rocket fuel, for instance, people working on reinforcing our tanks so they're less resistant to, or more resistant to IEDs. We have people who just do apprenticeships and sort of trades with us, which is also incredibly important. People flying drones, people flying satellites. And I went to a talk yesterday in Canberra where these people were talking about flying a satellite in 2024, which for me is super exciting. And we have other people doing things like developing more nutritious food for our troops. So a whole different science comes into DST, which I find really exciting, just in terms of general terms, but it's also really important for achieving our outcomes. But what I'm here to talk about today is actually what I'm doing, and I guess what is involved in the day-to-day life of a quantum technology researcher at DST. Well, I'm actually involved in a range of different quantum projects. So these range from sort of quantum clocks or atomic clocks to quantum communications to quantum sensing. And I just want to touch on 3 different projects I'm working on, one in each of those fields in the next sort of 10 or so minutes. And the first of these projects is one I'm working on for about 2 years now, which is developing a compact portable atomic clock. So the whole point of this project is to develop a better clock, better timing for everyone. Why do you want to do this? Well, I guess if you open up your phone right now and open Google Maps or Apple Maps, whatever maps you use, the reason that your phone knows where you are is based on a series of clocks in satellites at 20,000 kilometers above the Earth's surface, which we call the Global Positioning System Network. And these clocks have to be super, super precise because otherwise you wouldn't know where you are very well. So for instance, you've got a nanosecond timing error. So that's 1 part in 10 to the minus 9. So very, very small timing error. Your phone could think you're off by about a meter. If it's 10 nanoseconds, that's like 10 meters. That's a lot of distance that you can be off by. And on the flip side, if we can make a better clock that's better than a nanosecond error, we can know we are much, much better. And that's the point of this work. So we're developing sort of next generation atomic clocks. And these are effectively based on the quantization of atoms. So we have, in quantum mechanics, we take atoms and we say they've got set energy levels. So electrons can jump between certain bands in an atom. And one of these bands has a set energy. And the cool thing about this atom is it's the same anywhere in the universe. You can find the same atom, the same isotope, is the same anywhere you find it. So it's a really good reference. And what we do with this atom is we shine a laser at it, which is always fun anyway, but we shine a laser at it that's actually resonant with the energy of the atom. And what we then do is we count the number of cycles of that laser as it oscillates up and down in a second. This is really hard because it oscillates about 100 trillion times per second. But we have very smart ways of doing that. And by counting out those oscillations, we can figure out a time. It's like your second hand on your clock ticking around to get a minute. We're actually not just making one type of atomic clock, we're actually doing 2, because why just do one when you can do more? And so we have here on the sort of the table in front of you, this is us building a ytterbium atomic clock. So ytterbium, look down the bottom of the periodic table in the little bar sort of add in, it's in the lanthanide series down there, but it acts a lot like calcium, so a group 2 element. And here you can see a whole lot of different colored lasers. So we have a yellow laser to actually interrogate the atom and find that transition. We have a blue laser, which is actually cooling down the atoms to much lower than room temperature. And we actually have a green laser that you can't see under the shroud over here. It's actually finding out what state the atoms are in. So 3 different lasers for one clock, which is maybe a bit much, but it's going to be a really good clock. We also have here, which you can't actually see very well, so I apologize. In Emily's hand there, we have a rubidium atomic clock. So rubidium is a group 1 element close to the bottom of the periodic table. And it's a really nice element to use, and we can make a really nice atomic clock from it as well with only the one color just in the infrared. And down here, you've got a team from the ytterbium project. And I put these people on here because I really wanted to make a point that in experimental physics, the most important thing is actually working in a team. Doing science in a lab is really hard, and we need a series of different skills to make it happen. So I think on this project, we have currently 6 scientists, a project manager, and 2 engineers. And that's really important because what we've been doing the last 2 years is taking what we call these benchtop experiments, a thing that take up, well, can't see my arms now, but take up at least this amount of space, and trying to get these things out into the field. And that's sort of the point of my job, to take technology from the lab and put it into the field to find out where it can work and how well it can work. And over the past couple of weeks, I have a really great story on that. So I think it was only 3 weeks ago, the team, which you can see here in the background and me over here, we took these clocks, we put them into what we call Roadie racks. So these little black boxes here, which are actually the same sort of racks people use to move like amplifiers and things for concert gigs around. So we stole some of those and we put our atomic clocks into those. We've got one atomic clock here, one there, and then some testing comparison in the middle. And we took these out of the lab. We transported them 45 minutes out of the city to the defense base up there in Edinburgh. And within 2 hours of having them on site, they were working again. Now, I can't tell you just how amazing that is for a science experiment. Normally, we used to think working 1 day a month if we're really lucky. So taking these from the lab, putting them in a moving truck, bouncing along the pretty bad roads around the defense site, and then measuring it there is actually really, really exciting. And not just that, so we left them running it at the defense site for a week, as a bit of a proof of concept. Then we put them back into the moving van at the end of the week, and we actually ran the clocks while the van was moving the entire way back to the university. And that is just absolutely mind-blowing. And the reason that happened is because we had this team of people with a vast set of different skills on board. I should say, sorry, what I meant to say before, that so yes, I'm a DST scientist, but a lot of the work that I do is in partnership with Adelaide University. That's how we achieve the number of different things that we're actually achieving. So most of this team is a University of Adelaide-based team, with me being the only DST personnel included on it. The second project I wanted to mention is quantum secure time transfer. So it's great to have a really good clock. And if you have one, that's great, you know the time, but your friend somewhere else may not know the time as well as you do. So how do you help your friend out? How do you get them to have the same timing signal that you do? One way of doing that is what we call quantum time transfer in general. So I can send a laser beam with a timing signal on it between me and you. And that's really great. But it turns out that, you know, a secret hacker could actually get in there and send their own timing signal to your friend, and your friend wouldn't know that it was not you who was sending it. So it could really make you seem like you're somewhere else. And if you want to know what we call GPS spoofing and how terrible it can be, you should watch the Bond film Die Another Day. It's the whole premise of the film. But it turns out you actually easily do this at the moment. So for $225, I can make my own GPS spoofing device that can make you think you're somewhere else. And people use that, for instance, to catch rare Pokemon in Pokemon Go. So that's sort of the level of prevalence these things have currently. And we want a way around that. We want to be able to send a timing signal that people can't then spoof or make it look like it's from a different location. And that's where quantum mechanics comes in. So what we do is we create strings of pairs of single photons, so single particles of light. And we measure one locally, so at my site, and send the other one somewhere else and measure that. And by doing that over and over and over again, we can make a really, really precise timing signal. And it's not just precise, it's actually unspoofable. So due to the laws of quantum mechanics, if someone would try and measure that signal between you and your friend or put their own signal in, you could easily tell that and then disregard the signal you're getting. So it's a really powerful technique, but it hasn't really been developed very much yet. So again, as part of a team of people, not just from university this time, but also from industry, local industry, we did a trial of this in a dark tunnel at DST Edinburgh. So dark tunnel here being a sewerage pipe, an unused sewerage pipe, underneath a pile of dirt. And we sent this beam of single photons down the tunnel, just 50 meters long, and then bounced it all the way back to make a 100-meter total round trip link. And we send out our single photons using this little rig down here. So you probably can't see it very well. It doesn't look very exciting, but I find it very exciting. We're going to demonstrate that we could send these quantum time transfer signals over 100 meters. And that was a great proof of principle experiment. And now the next step for us is trying to expand that further. So go from inside in 100 meters to maybe outside over a kilometer, and then eventually, hopefully, between ground and a satellite. So that's another exciting project that I'm involved with. And the final one that I want to spend a little bit more time on is on quantum sensing. So we're going to use quantum mechanics for timing and communications, but quantum sensing is probably the most technology advanced part of the quantum space at the moment. And what we're doing at Adelaide University, with Adelaide University, is developing a portable quantum magnetometer. This is a device that can measure magnetic fields and measure them really, really, really well. And again, my role here has not been to develop the science so much. So Adelaide has been building these for about 5 years before I joined the team. But again, they took up an entire optical table. Again, you can't see my arms, but it was very big. And an entire rack of electronics, which is about my height and all the way down there. And it worked really well in a lab-based setting. But we want to get it outside the lab. We want to test it in the field and see how it works. Not just outside in the field, but underwater, which is something I have no experience in, or had no experience in until about a year ago. So my role in the project was to effectively build a sensor head. And that's what you can see down here on the left. So we have this glass cell here, which is full of rubidium atoms. So again, we're using an atomic quantum sensor. Essentially what happens here, in the presence of a magnetic field, the energy levels of rubidium will move ever so slightly. And if we were to put a laser beam, or maybe 2 laser beams in this case, through these atoms, we can measure that really, really tiny change. But for our sensor head, we had a bit of a challenge in that if we put any metal on the sensor head, it will perturb the magnetic field and we can't measure it properly. So I spent a lot of time learning how to 3D print parts in plastic. And you can see here some of my bits that I've made for the system. You can also see my terrible glue job. So everything is glued together with epoxy. And this is probably version 2. This is probably that long. I think we're now up to version 5 as we learn more and more about it and exactly the best way of putting it together. So after we built the sensor head, we then took it outside. This is us outside our building at the University of Adelaide. We're testing on this beautiful grass field. Here's the sensor head there. This is also the electronics for our system that is required to make it run. And probably the most important lesson we learned from going outside was that not all wheels are equal. So this is a nice, quite nice paved path. But if you run your electronics tracker over the top of that, it's quite heavy, and you have really bad wheels, you find out very quickly they actually disintegrate entirely. So the second time we took this outside, this wheel literally crumbled while we were pushing it back in. We had to carry the thing back into the lab, which was not fun on my back. But we've since gone to better wheels. You can see you've got nice red wheels now. But we still learned a lot from this in that, especially if you're going further afield, which I'll show you on the next slide, we couldn't use wheels at all. So we went to a sort of portable carry system. And I'll show you a problem we have with that in the slide. So cool, the thing worked outside, that was great. The next part of our work was to try and get this underwater. So by working with the ST group, we got hold of some underwater housings, which were really useful. So plastic underwater housings, again, no metal allowed in the sensor head. And then we had to find a way to firstly get signals to and from the sensor head underwater and not have it leak on us. So we worked on that with experts from the Maritime Division at DST. Then to weigh down the sensor head, because this is buoyant, unless you've added 5 kilograms of weight to it. And so we found a pretty dumb solution to that. So we actually 3D printed sort of plastic cylinders about this wide, and we filled them full of a 2-part setting epoxy that you actually buy from, I think, Bed Bath & Beyond. But it worked. So these things about the density of water, we put 5 of them in, and it sunk. And that was really exciting. And then with that, we took it and we tested it out in the field. So we took it out to the Ross Reservoir, which for those of you who aren't familiar with Adelaide, it's an hour northeast of the city. Here's a picture of it from Google Maps. And here is the boat ramp that we use to take the systems to and from the water. And now hopefully I'll show you a video of us after we've submerged our sensors, actually doing a test to see whether we can see a boat going over top of it. So hopefully this plays. So what you can see in this video are these 2 buoys here, an orange and a green one. And our sensor heads are about 20 meters below the water underneath these buoys. Here you have our test boat, which has got magnetic material in it. We have 2 people from Maritime Division who are driving the boat, and then me in the back being sort of useless, but very excited to be there. Got to see a very important scientific expedition. So bouncing up and down is obviously an important part of testing these things. And then we drove off. We actually did this 3 times. So we passed once and then twice, and then I think once through the middle of them. And we then got to shore and tried to look at the data, and we really wanted to see whether we could see the boat passing the sensor head or not. So this is a sort of make or break moment. And here are our results, which I'm really excited about. So the 2 different colors here represent the 2 different sensor heads we were using. And what you can see is that each time we pass, so time is here on the x-axis and magnetic field on the y, is that each time we pass, we have a little blip, an up-down blip. And so this firstly is incredibly exciting. The first time taking these things outside is amazing, and they've worked. But you also notice it's very discretized, like it's very digitized. You've got these step functions in there. And that's a problem to do with the fact that when we went from this full rack of electronics to just a carry side electronics, we had to make a trade-off between sensitivity of components and the size and weight of them. So here we've probably gone too far one way, and that's not sensitive enough for what we want, but we've made some changes since then, and we know exactly what we want to do to make that better. And we're hoping to go back out again by April or May this year and test it out with a better system and get better results. This is the whole point of science. They're always going outside, always testing, always making better. And that's one of the most fun parts of what I do. Cool, so that is, I guess, some of the projects I'm currently working on, and hopefully giving you a flavor of the physics that we're doing. But how did I get to here? So what was my path? I should say that I spent a lot of my childhood sort of moving around between Australia and overseas. My dad was a diplomat, but effectively every 3 years I came back to Canberra for 3 years and went overseas. By the time I hit year 11, I was back in Canberra. So I did my last 2 years, what they call college, I don't know what they call it in Victoria, in Canberra, and I studied math methods, so just standard maths, advanced maths on top of that. I did physics and chemistry, and I would have done biology as well because I just love science. But there were enough slots in the curriculum to do that. I did English, which I was always terrible at, and a minor in French. Once I did that, so I realized that I love science. I just enjoyed the maths. Well, I find the maths easy, and I really love the usefulness of the physics and the chemistry. So using that maths to do something with. So I then went to the Australian National University, which is just down the road in Canberra as well. And I did a Bachelor of Philosophy in Science, which is not about philosophy at all. It's actually an advanced science degree. And as part of this course, every semester, you got to spend one course effectively doing an advanced project. So actually doing quote unquote real research in a lab with a real scientist. And I put this picture here because while it's not a very nice looking picture, it means a lot to me. So this is my second year. I did a project building a laser. And this is the result here. Doesn't look great, but I was super excited. And through this project, getting hands-on with science, I learned that I love laser physics, so quantum optics, if you like. And that was really valuable. I love physics, but I didn't know which part of this I loved until that point in time. And that then led me to my final year project, my 4th year honors project, where I wanted to keep doing something similar, but slightly different. And I decided to do a project on quantum memory. So using atoms to store laser light, the information on laser light, then reproduce it later on. And that's when I fell in love with quantum atom optics. So it's more of a tongue twister, but definitely where I ended up with in life. And I love that honors project so much that I stayed around for another 4 years doing a PhD on the same project. And that was quite amazing. And after that, so at this point in time, I think by 2010, my then partner, now wife, had moved to Melbourne for her work. She's an engineer, so still STEM as well. So when I finished my PhD, I looked for a job in Melbourne. I was very lucky to find one new position in Melbourne with a group doing amazing science. My background was very useful, but the application was very different. So from sort of quantum information, I moved into biological imaging of particles. I was even more lucky because I got a sort of competitive position or a fellowship in Melbourne for another 3 years. And then luckier still that after that, I got a fellowship at Adelaide University in South Australia for another 3 years. And even more lucky that after that, I got a job at DST. So just when I finished my fellowship at Adelaide, DST were hiring in the quantum space for the first time ever. So I've been incredibly lucky during my career and worked with some amazing people at amazing institutions. Now, I want to take a slight detour for a minute because, I'm passionate about outreach. You are all the future of science in Australia. And I think science is amazing. I think everyone who can should be doing science. So over the years, I've been developing different sort of science experiments, hands-on science experiments, and that's really important. And not only has it been fun for me and fulfilling for me, but also led to some of the most interesting and exciting opportunities of my career. So just to give you an example of things I've worked on. So at the university, I built what we call a laser radio, a device to send sound information over a laser beam. And I'll show you a video from our first product testers on the next slide. While I've been working at DST, I've built what we call a laser maze. We use a laser beam over here, bounce off some mirrors onto a detector over there, and this light will change color if you hit the detector or not. And there's some mirrors that you can move along the way. So that's sort of fun and sort of still under beta testing, I guess we call it. And then even at a lower stage of development is a jelly waveguide demonstration I'm working on, where you use lasers and jelly to move the laser beam around and do cool things with it. And that's part of work I'm doing through the Australian Institute of Physics, which is a body all about spreading the love of physics, I guess, to everyone in Australia. So to quickly show you this video from the laser radio team, and so apologies if the volume is a bit loud, but hopefully it's fun. Sorry, I always love that video. I think it captures the gravitas of the activity that we've been trying to put together there. That's will lead me into the final two slides of my presentation. The first one discussing, I guess, my career highlights, and I've had a really great career and a lot of highlights. But I guess a couple of things I just want to point out. The first is travel. I love to travel, and a PhD and a career in science leads to a lot of that. So I spent 2 months in Paris during my PhD, which was absolutely amazing. I spent a month in Heidelberg in Germany, a month in Mainz in Germany as well, and done a lot of conferences overseas, including, I guess my highlights are probably Seoul in South Korea, and also on the ski slopes of Banff in Canada. So minus 20 degrees was not much fun. Next highlight of my career was actually being awarded the South Australian Tall Poppy of the Year award in 2018, which is both for science, but also for outreach as well. That was a really humbling experience, and I'm still trying to live up to that award at the moment. But it was really amazing to be there and to get that. Sort of both these things, so the outreach, the Tall Poppy, led in 2019 to me being invited to Google X, which is Google's moonshot factory over in Silicon Valley, where I got to set up demonstrations of optical interferometers to a whole lot of Google's top-level employees. And as part of that, I got to spend 30 minutes with Sergey Brin and Larry Page, who are Google's two founders, talking about gravitational wave detection, which is an experience I won't forget anytime soon. That was an amazing couple of days only, but definitely sticks with me. And the final, I guess, career highlight is again about travel. So due to, again, the outreach and my science, I was awarded a Fulbright Fellowship in 2019 to go spend 3 months working at Columbia University in New York City. So working with the top minds in the world in the field I was in, living in the most amazing city, frankly, I've ever been to. And I guess it's even more special because I finished that in November 2019, and a couple of months later, no one was traveling anywhere. So definitely appreciate that probably more because of that. I just want to finish up with a bit of advice to my high school self in terms of what I think about careers and the future. And the first thing is do what you love. So if you can't tell, and I haven't said it enough during the presentation, I absolutely love what I do. I'm always excited to get out of bed in the morning, even if sometimes it's earlier than I like. And I spend my days feeling like a kid in the candy shop. And I hope that you can all experience the same thing with your lives. Life's too short otherwise, and I think STEM careers can be incredibly fulfilling in that regard. Secondly, the future of STEM in Australia is super exciting. So when I finished my PhD, the only real jobs for me were in academia. That's not the case anymore. Even if you want to stay in Australia, there are a number of sort of startup companies, as well as big companies like IBM and Google, who are hiring quantum specialists to do really cool stuff that's getting out of the lab and actually being useful in the field. So if you get into STEM now, there's no knowing where you could end up. And the final point is not really advice, but more a plea. We need you. We need more Australian STEM graduates. So I heard the other day the Australian Space Agency needs 20,000 space jobs by the end of 2030. And in terms of the quantum area, we need 16,000 new jobs by 2024. So hopefully you can help us be part of that and help us fulfill these numbers that we need to get to. With that, I want to just finish off by acknowledging all the people here who've helped me achieve what I have achieved today. Like I said, sort of midway through, science is not an individual pursuit, it's being part of the team. I've been very lucky to have many great people as part of my team over the years. Thank you very much for your attention.
Thank you so much for that. Ben, I really, yes, your love of physics and quantum has definitely come through in that talk. Me being not from a physics background myself, I'm even excited about it. So that's definitely a turning hearts and minds here. I did want to start off with the kind of collaboration and the teams that you've worked with, because you have worked across a number of organizations. And is the people that you're working with, is that important to how the work goes and where you find yourself, what you find yourself working on? How important are those people to your choices and what you're working in and on?
They're incredibly important. I guess my favorite example, so when I was at Melbourne University, I worked with an amazing professor there. And when I was finishing up my fellowship with Melbourne, he asked me, what do you want to do with yourself? And I said, I want to stay in Melbourne and work here. And like, no, you don't. You want to go to Adelaide. Adelaide's great. Go to Adelaide for 4 years. And I thought at the time he was trying to get rid of me, but actually he was trying to help my career and push it forward that way. So I had some very supportive sort of team members and people to work with. But the other key thing about teams is having different viewpoints on things and different areas of expertise. So I think the clock project I'm currently working with is a great example. We have 9 people on that project. It's a lot of people. So 6 scientists, like 4 for one clock, 2 for another clock, 2 engineers, and that's really important because as a scientist, if you come to something practical, I'm absolutely useless. I can't set anything up, IKEA stuff will fall apart if I put it together. That's not where I'm good at, but this is where they're good at. And finding engineers and scientists who can talk to each other and have a common language is harder than you would think. But if you can do it, you can achieve amazing things. And so having teams with different expertise but being able to communicate between those different areas is incredibly important.
Yeah, I've heard that. Yeah, there's definitely a different language between engineers and scientists, which you wouldn't think, but those who get it right do it really well. And I think physics do it really well, very close to it. With you talked a little bit about the travel that you've done and going in people overseas. Do you do a lot of collaborations overseas, or is it pretty much within Australia, or a little bit of both?
It's a really good question. So I think I'll start by saying that the sort of quantum community in Australia is really tight-knit and is really supporting, and it's not competitive at all, which is really great. We're too small to compete with each other. So I work a lot with people in Australia, obviously, but then I think it's always good to try and collaborate overseas. So I guess one thing I didn't say in the presentation is, so I have what we call the two-body problem, in that I have a wife who's absolutely amazing at what she does. She's also in the STEM field, but she needs to work in Australia to do what she's doing. So I've looked for opportunities to get jobs in Australia. You can still get amazing science jobs in Australia, but at the same time, it's still worthwhile looking for collaboration opportunities overseas. And that's what led me to work in mines for a month, looking at cold atoms and hollow core fibers, or to work in Paris for 2 months doing quantum memory work over there and learning from what their expertise and what they do better. And I think the thing about experimental physics is if you can't go and see the lab, you don't get as much out of it, because it comes down to, oh, use that bit of kit, that's really cool, I want to use that. But it can come down to that sort of stupid level of detail. If you don't go visit them and deal with them one-on-one, you don't get that. So I think these last 2 years, while Zoom conferences and things have been a lifesaver, they're definitely not the same to going and visiting the labs and the people and talking one-on-one. So you're always looking for those international linkages with these projects.
Yeah, we're all hoping that will resume quickly. All of our audience, don't forget that you can put any questions into the Q&A at the bottom of the screen. We're always keen to take questions, but I always have lots of questions, so I'm in. With you were talking a lot about transporting things from one location to another, and the wheels breaking and everything. How important is it for these I guess the things you're working on to be transportable and to be moving somewhere else rather than in one building?
Yeah, so I guess that's really a function of my new job. So moving from academia 2 years ago to defense, the focus is much more on, can we deliver these things? So for many years, we've promised quantum mechanics will change the way we compute, the way we communicate, the way we sense anything. That's all well and good. And if we can do it in the lab, that's fantastic. But the technological channel, getting things out of the lab and into the field is immense. And if we can't demonstrate that, then we can't push these things forward. And so for me, it's been a really big challenge to try and move from a fully quantum scientist to a semi-quantum scientist engineer. And as I said, I'm a really bad engineer. But trying to bridge that gap and bring it out of the field. There's interesting science in there, but there's also interesting sort of electronics has to be done to make things work small and well. Computing to be done to make things operate by themselves. All these things are incredibly important if you want to demonstrate that these things can actually do what we're saying they can do. And we don't want to end up like nuclear fission. Whichever one it is, it's been always 30 years away for the last 100 years, or we don't want to end up like that. So if we can demonstrate these things outside the lab, that's incredibly important, but does take a change in mindset.
Yeah, and you do kind of bridge what is traditionally academia, which is University of Adelaide to work with, and DSTG, which is, I guess, industry. That focus is a bit different. Have you seen that the people who work in each field are slightly have different foci, and that's a different thing to bridge? Or?
Absolutely. So what I would say is, it's ready to go outside, and I'll show it to some people in the Army or the Air Force, and they're like, no, it's not, made by a big company, have a sticker on the front saying this works perfectly every time. They don't want it. So just different levels of expectations for various things is one part. But also the timeline that we can work on. So academics normally working on a 2 or 3 year time frame, because that's for the funding being provided for. Running on a shoestring budget, not cutting corners, but saving every penny we can by being really smart about it. Working for defense, on the other hand, the budgets are normally quite bigger, much bigger. The timelines are much longer. People are thinking much further ahead because we need to build capacity in sort of 5-10 years for the Army and Air Force in places. So that's really welcome, looking at a longer term view of things. So it's not ready now, but give us 5 years or 10 years and we can make it ready. And they see that and they support that. And that's a really valuable mindset shift for myself, but also for the project I'm working on.
Yeah, and both sides are needed, the academic to start it and the industry to deliver it and find somewhere to use it. There's no point having it in a lab.
Absolutely.
It doesn't do anything. A little bit of a step back to kind of school and high school, you did do a lot of kind of maths and physics and things. What were the sorts of things that caught your imagination when you were doing high school physics? What things kind of drew you into it?
I think it's always the fact that you could sort of predict the future in a way with physics. If you have a sort of problem where you're throwing a ball some distance and you let it go with some force, you can calculate where that's going to land and you can know the future in that way. So just maths can help predict how everything's going to work and how it all evolves. So especially at the time before I did quantum mechanics, the idea of sort of Newton's clockwork universe, that if you knew where everything was and where it was all moving, you could predict the entire future of the universe. It was really appealing to me. I like that order, I must admit, in my life. I like to have things behave as they should and be able to describe it with mathematics, which is probably why I don't work with people as a subject. I work with people in the lab, but I don't do experiments on people. And they think for themselves is sort of well beyond what I can deal with. But the controllable nature of physics and understanding what it can do, and then just for me, the challenge is then making it do it. So smart people do all the theory behind the quantum stuff that I don't understand, but I can take that theory and I can put it into practice in the lab. And that's really fascinating for me, because some esoteric equations and then you make it work and actually do a thing. That's really rewarding.
It's always like, yes, it worked.
Yeah, which one day out of a year or so it will work, and that's very exciting. But a lot of building up in the meantime.
Was there something else you thought you might have been when you were at high school, like another path you might have ended up on?
Look, to be honest, I was really tempted at the end of high school to apply for law school, just because that's what people did, right? You get really good grades, you go to law school, you earn a lot of money. And I think my parents had a chat to me like, Ben, you hate writing anything. You hate English, you hate writing long essays. Why would you do that? And then I realized that, yes, that is a stupid thing to do. I should do what I actually enjoy. And I've always enjoyed science from an early age. And just thankfully, I was good at the maths, which is always like the core of a lot of it. And so that was, I think, one of those crossroads in life where I could have gone down one path, but I'm so incredibly glad that I didn't. The one sort of thing I regret is that I nearly studied music at university as well. So I was going to do a joint degree in science and then in the bassoon, which is something I was playing at the time. And I sort of really wanted to do it, but I had chat to my music teacher. He's like, so in 4 years, I can make you an okay bassoon player. And I thought, okay, it's good to have the realistic advice from someone. I can probably be a good scientist, but a really bad bassoon player. So let's just go with the science for the moment. And I sometimes regret not spending more time learning bassoon and doing those sort of things.
They do say people who do maths quite well play instruments quite well.
Doesn't apply to me, unfortunately.
Found an exception. It's great. My kind of favorite question to ask scientists, particularly when we're doing careers in STEM and things, is what do you do when you're not doing science? Maybe playing the bassoon isn't one of them. Not
at the moment. My mother's very disappointed in me for that. No, so actually, I like to do science at home. So science ends up being a fully life-encompassing thing. So at the moment, I'm doing little projects with Arduinos, these little microcontrollers you can buy off the internet for like $20 and get you one with Wi-Fi on it. And so I've got one that is currently monitoring my house. So you can see people move in certain rooms and the temperature in certain rooms. My parents have a coast house that keeps getting flooded when it rains, which is not great. So I built my dad a moisture sensor for the house that's connected to their Wi-Fi, and then via the internet will let me know if the house is too wet or not. I recently built a driving car park sensor for my garage. Again, practical things I'm not good at. So I keep running the car too close to the front wall of the garage. So I built this device that will have a little proximity sensor at the front and a little LED wheel at the top. And as I drive the car closer to the front of the garage, it will light up for green, orange, red, and start flashing at me when I get too close. So I do a lot of those things in my downtime. I'll build more of these outreach experiments. That's what I love to do with my spare time. Or play video games. But, yeah.
It's not a bad use of spare time, I have to admit. The sensors and things are definitely something a little bit more than my skill set. But I've really enjoyed listening to you talk about what your work is and journey and where you've got to, and your, yeah, obvious excitement and passion for physics, and how great physics is here in Australia. So thank you so much for coming on the Shape Your Future series with us, and we look forward to seeing more of your laser clocks and things come out and help everybody, not just defence, in the future. So thank you all for joining us. And if you please fill out the feedback form you'll get from us in the emails very shortly, and look out for those worksheets, because there's definitely a lot more about Ben's work in there, and you can find out a lot more what he's doing, including the laser radio as well, if you're interested in that too. So thank you all for joining us today.
Thank you very much.